Thank you everyone, and also for giving me the opportunity to present my work today. So I will talk about proving dark energy with cosmic voids. And so let me start with some motivation for this talk. So as we know, dark energy remains the biggest unknown of modern cosmology. And we were able to probe its equation of state. But however, this by looking at the, the universe expansion, but this alone is not enough to tell us what is the nature of dark energy. So if we want to understand its nature, we need to have access to more information. And this information is encoded into the formation of the cosmic structure. And so this is why we are investigating a lot of time and energy in large-scale structure survey, and we have been able to predict quite accurately the clustering properties of galaxies on small scale. We are looking also at lancings. But in this big picture, we should also consider cosmic voids that play an important role. Furthermore, we might wonder if we are not washing out some useful information when we average cosmological probe over the entire sky. For instance, we might consider to look at some cosmological probe in under-dense versus over-dense region of the universe. And in fact, that might be particularly relevant to test for modified gravity theories that rely on the so-called screening mechanisms. As we mentioned already, this mechanism allow for deviation of general relativity in on the dense region. And this is why cosmic voids could potentially play a central role to reveal the nature of dark energy. So, of course, in order to further investigate the cosmic void, I think we still need to do quite a bit of work on developing some accurate theoretical prediction that we can compare with observation. And so in this talk, I would like to address those three questions. The first is how can we predict the evolution of the void density profiles for non-standard cosmologies? The second one is the growth rate that we probe in on the dense regions the same as the growth rate in averaged region of the universe? And the third is, can we accurately model redshift space distortion around voids? So to address this first question, I would like to present one of the work that I've done, and that allow you to have a quick estimate of the imprint of non-stellar cosmologies using a method of using a Monte Carlo random walks. So the idea is the following. You can write the evolution of the linear density field smooth on some scale R, and this follow this stochastic equation where delta k here is the stochastic variable, which for Gaussian initial condition is defined by the linear power spectrum. So you can, and the W is the filter function. So you can solve numerically this equation once you specify initial condition, and you can solve this equation for several initial realization of your density field. So this is an example where you start on large scale, where the density contrast is 0, and this is for three different initial realization delta k. And when you solve this equation numerically, you end up with this blue curve. So this method is not new. It has been proposed within the excursion theory framework to predict the abundance of halos. What is new is that what I've done is that I took a log normal transformation of this delta variable. Why? Because we know that today, from an empirical point of view, the one-point distribution of the matter is well described by a log normal PDF. So by taking a log normal transformation, you end up with those random walks that are shown here in black. And then to do this transformation, you need to know the linear as well as the nonlinear power spectrum. So why did I do this, this log normal Monte Carlo random walk? I think there are a few interesting things that you can do with this method. The first is that I was able to quickly generate the imprint of modified gravity f of r type on the void density profiles. So basically I generated, I don't know, 10,000 of those initial random walks out of which I selected only those that I believe are representative of a void. So I selected a few criteria on the density bin. So for instance, this one, you see at when the radius is close to 0, delta is -1, and then it's go back smoothly to 0. So out of those 10,000, maybe I have only 100 that satisfy those conditions, and then I take the mean value of them, and then I end up with those curve here. And here is for two different, so this is for a lambda CDM model, and for an f of r model of -10 to the -4. And you can see here the relative difference. And you find that remarkably, you find the same trend as what you would find if you look at a full n-body simulation to analyze those void density profile, which is that for f of r gravity, the voids are emptier at the center, and they are a little bit more clustered at the ridge. And that also depends on the type of void, but you can also, if you want, select the voids that enhance the imprint of this f of r model. And other things that you can do is to look at the evolution of your void density profile as a function of redshift. And so this is preliminary result that we are investigating with my collaborator, where we have compared this Monte Carlo random walk method with the spherical evolution prediction. The thing is, with the spherical evolution, you need to know what is the initial density profile to predict the density profile at later redshift. While with this method, you can go back in time. You start from the z=0 observed density profile, and you can go back in time. And then I think there are other interesting things that you can do with this technique, but I'm not going to talk about for this talk. All right. So if there is no question, I'm just going to go to the second part of my talk, which is how my collaborator and I have tested the consistency of the growth rate in the 6DF galaxy survey. So to do that, well, let me just tell you so that we are clear. So the linear growth rate is defined as the logarithmic derivative of the growth with respect to the scale factor. And this is sensitive to both the background expansion as well as the gravitational forces. And this is why it is a crucial cosmological probe that can allow us to distinguish between different models of dark energy. So how can we probe the linear growth rate? There is one direct way, which is to measure directly peculiar velocity, but of course it is more challenging. Why? Because peculiar velocity are sourced on large scale by the gravitational potential, which is directly proportional to the linear growth rate. But again, this is challenging to directly observe peculiar velocity measurement. So alternatively, we can look at redshift space distortion. And so here I'm showing this well-known pattern. When you look at the galaxy-galaxy correlation function in redshift space, you will see that there is an elongation along the line of sight, known as the finger of God, and on large scale you see this Kaiser effect, which is directly modeled as a function of the linear growth rate. Now you can actually observe the same sort of distortion if you look at the galaxy void correlation function along the line of sight and perpendicular to the line of sight. And so to model it, we used the same model that was introduced by Peebles in '93, or in the Gaussian streaming model of Fisher in '95, where you basically do a convolution between the galaxy void correlation function with the distribution of the galaxy, the peculiar velocity of galaxy around your voids. And so for this distribution, you can assume a Gaussian distribution, which is described by a mean value and a standard deviation, and the standard deviation is this so-called velocity dispersion sigma v. For the mean value, we assume this linear approximation that is directly linked to the linear growth rate f. All right. So the 6DF galaxy survey is a low redshift survey, which is good because we want to probe the late time acceleration of the universe. It has mapped nearly half of the southern hemisphere, and it contained a catalog of 100,000 galaxies. So we have used this survey, and we have tried to probe the growth rate using both the galaxy-galaxy and the galaxy-void correlation function in redshift space. And so first we have tested our method on MOX to ensure that we recover the fiducial cosmology for the growth rate. So this is what we have done is we have assumed a lambda CDM cosmology, a linear bias, as well as a constant velocity dispersion and a fiducial void size. And this is the fiducial cosmology for F sigma 8. And you can see here the blue ellipses correspond to the constraint that come from the galaxy void, and the red ellipses from the galaxy-galaxy correlation function. And both nicely agree with the fiducial cosmology. And then we have applied all of this pipeline to the 6DF galaxy survey. And we have found a consistency with lambda CDM with a f of sigma 8 of 0.36 plus or minus 0.06 for the galaxy-galaxy redshift space distortion, and 0.39 plus or minus 0.11 for the galaxy void redshift space distortion. So you can see that this error bar here is about twice as much as this one, and this is mainly due to statistical error that should shrink with upcoming survey. So to compare this work with, there is two other group that has used redshift space distortion around voice to probe the growth rate. One from Amos et al. That use SDSS data, and one from Oken et al. That use the Viper survey. And what they have found is roughly a consistency with lambda CDM, even though here there might be some something going on at low redshift, but I can't really talk for Nico's work. And here in the case of Viper survey, they find a value that it's, I think, consistent at 2 sigma with lambda CDM. So I should mention that in my work, as well as in their work, we use a very simple model to describe this redshift space distortion around voids. And I think we might be more careful about testing all of the hypotheses that I enter in this model. And so in this work, I try to test if it was a robust model to really infer the value of the growth rate without introducing any systematic error. Also, because with upcoming survey, the systematic error will be important. Right now, we are dominated by statistical error, which will not be the case in the future, so we need to have very accurate model. And so just to briefly introduce what I've done, I wanted to see if the Gaussian streaming model with this simple equation that I've shown you is a robust model for describing just dark matter density field. So there is no complication due to the bias. In this case, it's simply the dark matter density field. And I wanted to test the sensitivity of the different void type to infer the value of the growth rate. So what I've done is that I fixed the void's size to a fiducial fairly large value, but then I selected void that has different profile. You can see the amplitude at the ridge is different here for 3 different void size, S1, S2, S3. And then I tested the first linear approximation for this describing this the velocity profile around the voids. And you can see the result here for the 3 different void profiles. So the dots are what I measure in the MOX, and the dashed line are this linear approximation. And you can see that when you are at the center of the void where delta is close to -1, this linear approximation doesn't do a great job. So in order to fix this, I propose to introduce this sort of semi-empirical correction to it that depend on the second order growth rate, and also delta 2 here can be expressed as a function of the void dark matter correlation function. And so to see the impact of this this offset with the linear approximation in the derivation of the growth rate, I have used the assumption that we have previously used, so linear approximation and a constant velocity dispersion. And for these 3 different void size, I infer the value of the growth rate as a function of the fitting range, Why? Because, for instance, in Chai et al., the author have shown that when you have a density profile that is close to -1, you should expect that this linear approximation breaks, and so you should introduce a cutting scale around the void when you perform your chi-square. And so you can see indeed that the inferred value of the growth rate in the MOX, so this is the fiducial value, and you can see that if I don't have this fitting range, the 3 different void size leads to 3 different value of the growth rate that are, well, maybe consistent with each other, but it's not. It's a lot of scatter around it, unless you consider a large cutting scale. And now I repeat this analysis, but using this time this semi-empirical correction that I proposed, and I used the exact velocity dispersion, not a constant. And here you can see that now you have some of a nice agreement between your different void sample. So they are within 1 sigma, and they are less sensitive to this cutting range. Now, I also wanted to see if we could use redshift space distortion around voids to test for sort of quintessence type of dark energy. And so I repeated this analysis using numerical simulation from this Deus consortium website. And basically, I used the same void finder that looks for specific shape of the void density profile in my lambda CDM simulation and my quintessence type of dark energy. So the void in real space, the void dark matter correlation function is very similar. Also the mean velocity profiles around the void is very similar. Interestingly, the velocity dispersion shows an imprint on this quintessence type of dark energy for this type of voids. And you can see here also that there is a variation of the value of sigma v depending as on the scale from the void center. It's not just a constant, even though after the ridge it goes toward a constant value. And then I'm just going to give you briefly the main result. I run the chi-square over this 2D measured correlation function to infer the growth rate, but this time I also let sigma v as a constant parameter. And what I found is that if I use this linear approximation, I end up with this dash ellipses. So this is for the RP-CDM and this is for the lambda CDM. The blue dash here is the fiducial cosmology for the quintessence type of dark energy, and the red one is for the lambda CDM model. And you can see that there is some sort of a systematic offset. The band, the band here for sigma v shown the average mean value of this measurement. And you can see, yeah, so that's it. And then once I implement this semi-empirical correction for the velocity profile, I recover the fiducial cosmology. So this is the solid ellipses here and there. So just to conclude, so I think testing the cosmology with cosmic voids is something that is relatively new, but that can be very powerful, potentially to reveal the nature of dark energy. And to do that, we still need to develop a more accurate prediction of the void statistical properties. So here I presented you some sort of new technique that predict the void density profile, but you could extend this sort of work to predict the abundance of voids or other things. I also shown you that now we are using cosmic void to probe cosmology, and here I presented the work that we have done with the 6DF galaxy survey. But this is still currently in good agreement with lambda CDM, but as upcoming survey will arrive, we will need to, this will reduce the error bar, and then it might be interesting to see if there is some sort of a deviation from lambda CDM. So you can check out the Taipan survey, which should start taking data quite soon, where we will repeat this analysis. And finally, I think, again, the big con with the looking at cosmic voids is that it is relatively new. So right now we are using very simple models that will need to be improved as statistical error will shrink. Yeah, that's it.
Hi. Hi, thanks for the talk. So I have a question. So in 2012, with collaborators, we had we had published a paper on how to test dark energy modified gravity with voids. And I remember that one of the main problems was the start, in the sense the definition of the void that basically changes completely your result. At that time, we were using the watershed void finder. And in addition to that, as you mentioned also, there was the problem of the bias that basically was affecting a lot, and also the statistics, in fact, whatever data sets you use at the moment. Yeah. So I didn't understand how the situation in terms of all these problems improved, in particular in terms of the definition itself of the void. Because at the end, it seemed that the effect on the growth that on the sigma 8 that we were finding was basically difficult to attribute to the actual model.
So I think we all have different method. So for instance, in Amos et al, they have this sort of watershed void finder as well, with sort of a void profile, but they also fit for the bias. What we have done is slightly different. So basically, we separate the dark matter void correlation function to the galaxy void correlation function. So we calibrate in this work at least, we have calibrated this. So this is a dark matter void correlation function. And we calibrated this one on our MOX catalog. And then we were able to test, and then to test if just a bias time this function could reproduce the one of the galaxy MOX, right? So, and we found that, in fact, even if when you fit for it, for this bias parameter, the value that you get is very consistent with the one you get by fitting the galaxy-galaxy correlation function. So it's not a crazy value of the bias that you get. So you can sort of dissociate this two. I don't know if I answer your question. Yeah.
Just want to add a comment that it is true that there's a lot of uncertainty in the void definition, but this is probably not surprising given that cosmic web is a very complicated structure. So I think the things that probably the way to do it is to try different void finders and make sure that you apply the same void finder in real observations and in your simulation catalogs to make sure that you can compare theoretical prediction with observations, just to be precise.
Okay, so thanks again, Sandra.